In this video, we're going to discuss standard temperature and pressure, and then the ideal gas law. Standard temperature and pressure is it's kind of like our baseline, and it states that we can predict the amount that a volume that a gas will have, regardless of its identity, honestly, which is really cool. Based on if we look at its temperature and pressure and holding these constant. So standard temperature and pressure refers to 1 atmosphere of pressure, which is 760 millimeters of mercury, and 273 Kelvin, which is the same as 0 degrees Celsius. So these make up standard temperature and pressure, or STP. Now, at this temperature and pressure, we'll see that 1 mole of any gas, nitrogen, helium, hydrogen, oxygen, it doesn't matter, will have a volume of exactly 22.4 liters. And we refer to this 22.4 liters as its molar volume. It's the volume of 1 mole of gas. And this is interesting because it's only gases that we can see the exact same behavior regardless of chemical identity. And that's because these particles are so far apart that they're not interacting. And that means that we can predict the volume or the number of moles or the pressure or temperature for any gas, knowing a little bit of information about it. And it doesn't matter what its identity is. And so that brings us to the ideal gas law. And this is an equation that connects the 4 properties of gases that we introduced: pressure, volume, moles, and temperature. And we call this equation the ideal gas law. And I usually remember it by remembering it's Puvnert. So I just kind of spell it out, and it's silly enough that it sticks in my head. Puvnert allows me to calculate either pressure or volume or the number of moles or temperature of a gas as long as I know the other 3 variables. Now you'll notice there's something else in here, and it's R. That's not one of our variables. So we learned from our combined gas law that we can say that, let me write this out. So we had PV1 for T1 equals P2V2 over T2. Instead of thinking of this as a quality, we can think of this as instead things being proportional. So I could say that pressure times volume is proportional to temperature. And then we learned from Avogadro's law that pressure and volume will also be proportional to the number of moles. And so this relationship right here is what leads to our ideal gas law. And R is a universal gas constant. It is the number with units that makes this proportionality become an actual equation. So I can actually calculate what pressure is as long as I incorporate this R value, which makes pressure and volume equal to temperature and the number of moles once I incorporate R. Oops, change the screen size, my apologies. There we go. So what R is based on the units that you're working in. And I'll give you these values for atmospheres or millimeters of mercury, and you don't need to memorize them. You just need to know how to use them. So for atmospheres, R is equal to 0.0821. That's its numerical value. And it has units of liters times atmospheres divided by mole Kelvin. This is not an equation. These are the units. A lot like miles per hour when you're driving down I-5, units can have more than 1 unit attached to it. And this one is really complicated. It's liters times atmospheres all divided by moles times Kelvin. And it has a complicated set of units. So that way, if you plug in any one value or if you're trying to calculate one value and you plug in 3 others, your units will cancel out with R, so that way you have just the unit left for the value you're trying to calculate. So R has complicated units, so that way you can calculate a number with the correct units using the ideal gas law. Now, for millimeters of mercury, it's a little bit different. It's 62.4. And you'll notice the real difference between these. It's a different numerical value, but the pressure units are different between the two. And so you can convert these two R values into one another using the conversion factor. 1 atmosphere equals 760 millimeters of mercury, if you like. So when you're using the ideal gas law, you choose an R value for the units of pressure you want to use or calculate. I'm going to walk through an example of this here. And later there'll be an opportunity for another example to try on your own. So if we collect 0.0 or 0.1 moles of carbon dioxide at room temperature, which is 298 Kelvin, in a 500 milliliter closed system, so like a flask with a cap on it, that had a vacuum on it, so it was originally at 0 atmospheres. What is the pressure of carbon dioxide in the container? Like all word problems, I think it's important to extract out the information and write it out so it's easier to develop a strategy to solve the problem. So I'm told that my number of moles equals 0.1. My temperature equals 298 Kelvin. I have a volume equal to 500 milliliters, which I'm right away going to convert into liters by dividing by 1,000. So I have 0.5 liters. And pressure, I'm told it's initially 0, which is that there's nothing, and I want to calculate what it is after we collect 0.1 moles. So this language is a little misleading. The pressure is not equal to 0 at the end of the experiment. It's just before I add my CO2. So what I want to do is calculate pressure. So that means I will need an R value. I can use R is equal to 0.0821 liters times atmospheres divided by moles Kelvin. If I want pressure units in atmospheres, or I could use R is equal to 62.4 liters times millimeters of mercury divided by moles Kelvin if I want millimeters of mercury. I'm going to go ahead and use atmospheres. So my equation is PV equals nRT, and I'm just going to plug into that, knowing that I'm trying to solve for pressure. So pressure times 0.5 liters equals 0.1 moles times 0.0821, and that's liters times atmospheres divided by moles times Kelvin for my units, and then times 298 Kelvin. So I'm going to isolate pressure on one side by dividing both sides by 0.5 liters. And I want to show how the units cancel here. So I'm going to take a minute to rewrite this. And I know it takes a lot of time to write out all of these units, but I strongly recommend it because when we stop relying on units for problem-solving strategies, we kind of just end up guessing. All right, so look at this. If I were to just extract out my units from this, they would be moles times, let's get a little more space here. Let's do this right here. So looking at just my units, I would have moles on the top times liters times atmospheres divided by moles times Kelvin, and then times Kelvin for my temperature. And this would all be divided by liters. So looking at what cancels out here, moles is on the bottom and on the top. Kelvin is on the bottom and on the top. Liters is on the bottom and on the top, leaving me with units of atmospheres for pressure. And so that's why we've got those crazy units for R. And so if I plug this into my calculator, I'm going to get a value of 4.893 atmospheres for my units. It's kind of a lot.